Okay, and we're back as I said I would be after the exam. It is currently approaching 1 a.m. right now, I'd say. Let me check here. Yeah, it is 48 past midnight. So, yeah. I was planning on filming this much earlier in the day, like possibly in the early afternoon-ish, like as soon as I finished my exam. But I took a nap, went to the library, met some friends, and now we're here. But what's important is I'm filming it, and that's not just another empty promise. But okay, we're here now. So we're here to discuss the linear algebra paper I did today. It was 3 hours, starting from 9, ending at 12. When I first heard the exam was going to be 3 hours, I thought to myself, that's way too much time. I'm going to be done in like an hour 45 and I'll leave early. Yeah, I needed the full 3 hours on this one. Um, but that's not to say it went badly. I do think I did pretty good. I was actually able to take the question sheet home with me, so that's great. We can look through some of the questions now. So yeah, nothing too bad here. Row transformations to show the RREF of A is that. Yeah, I was a bit nervous at first, but once I got into the swing of things, this was much quicker. Um, for this one, hence show that det of A equals 0 and the rank of A is 2. I couldn't really show it. I just kind of explained the fact that the det of a matrix, that the det of a matrix is not equal to 0 if it is full rank. B is A is clearly not full rank as it has 0 rows in its RREF form. Therefore, that is 0. I don't know if that's really showing that. Then I might use a similar kind of explanation for the rank of A equals 2 question here, part C. I just kind of said that the rank of A will be equal to the number of non-zero rows in its reduced row echelon form, B here. B has 2 non-zero rows, therefore the rank of A is 2. Yeah, I don't know if I got those marks or not. I explained it, but I didn't really show it like mathematically. So I wouldn't be surprised if I lost like 1 or 2 marks on these questions. Next page here. Oh yeah, this wasn't too bad. Show that the solution of the equation. Oh, let me get this on the page here. Show that the solution of the equation 1 can be written as. I mean, this one was fine, honestly, as well. It was just a case of putting this, yeah, of multiplying A by this here, as it says, and then I'm getting the equations from that and putting it into like vector form. You end up getting 2 free variables here because of the 2 0 rows here. Yeah. Yeah, so these two, so u and v end up being your free variables, and then you just say let s equal u and v equal t to get these vectors here. This one, I remember this one taking, even though it's only 4 marks, I remember this one taking me a while to figure out. I should have said the entire paper is out of 100 marks. The first 50 marks are based on what I did in autumn time, which is mainly focused on matrices, and then the second 50 marks is focused on what I did in spring term, which is mainly focused on vector spaces. So yeah, I should have said that in the beginning though. Okay, but yeah, for this question, this one wasn't too bad. I remember having to I did x, y, and I did x times the first column of the matrix, y times the second, u times the third, v times the fourth. Then using this here, I like subbed in, I put these coefficients also in that equation, and I believe I had to let s equal 1 and t equal 0 to get this equation, and then I had to let t equal 0 and s equal 1 to get this equation. I may have got that the wrong way around, but it was something along those lines. Okay, I remember when the first time I looked at part I looked at it for a good 5 minutes and I just couldn't figure it out, so I had to come back in the end. I did figure it out there, but it wasn't even that bad. I believe I just had to. I think it's that I had to let T and S be equal to 1 so that the C2 gets cancelled out of the equations there. So yeah, if you look at the second components here, if S equals 1 and T equals 1, add these together, the second component in these vectors, I should say, becomes, if you add them together, -1 plus 1 is obviously 0, so that cancels out the second column there. That's what I believe you had to do. Okay, and now on to approved questions. This one was fine. I believe I went something along the lines of saying that the identity is equal to the transpose of the identity, and that's equal to A times A minus 1 all transposed, and then like I said that is equal to A minus 1 transposed times A transposed, and I said that since A minus 1 transposed times A transpose equals the identity matrix, they must be the inverse of each other. That's what I did for that one. Part II. This one wasn't too bad either. Yeah, I said that the det of the identity matrix is equal to 1. Therefore, the det of A times A minus 1 is equal to 1. Then I used the fact that you can split that det up into two separate dets. So I said det of A times det of A minus 1 equals 1. So therefore, det of A equals 1 over det A, as shown. I remember this one taking me a little while because I actually forgot what orthogonal meant for a second. At first, I thought it meant that the transpose is equal to the minus of the original matrix, but no, that's skew symmetric. Funny that I thought that, because actually skew symmetric has only ever come once in an assignment, like at the beginning of the year, so I don't know why I still remember that, but yeah, I remember that orthogonal matrix meant that the transpose is equal to the inverse. And yeah, I can't exactly remember what I did for that one, but I'm pretty sure I got that one correct though. I remember being confident in my proof for that one. Yes, this question here. Okay. I'd say out of the entire paper, I was confident I'm 100% confident on these first 12 marks here. So the eigenvalues of A are -4, 1, and 6, that was completely fine. Eigenvector, but that was completely fine. And the eigenvector for -4, that was completely fine. This question here, prove that 2 is an eigenvalue of the matrix B defined by that. So for this one, my first thought immediately, for some reason, was to use the Cayley-Hamilton theorem. Like get the characteristic polynomial for this matrix and use Cayley-Hamilton to like get the inverse of A, and then substitute that into there and the inverse into there, find B, and then get the eigenvalues for that. Then I saw this is just 6 marks. I thought to myself, that's way too much work for 6% of the paper. So I just ended up deciding that what I did was I still used Cayley-Hamilton, but I didn't find the inverse of A. I think what I did was a little bit abusive, actually. I said something along the lines of, what was it again? Oh yeah, I said that Cayley-Hamilton states that a matrix satisfies its own characteristic equation. And remember, I minus b from both sides to get a squared plus a minus 1 minus b equals 0. Then for a I subbed in lambda a, so then for b I subbed in lambda b into this equation. So I got lambda a squared plus the reciprocal of lambda a minus lambda b equals 0. I chose the eigenvalue 1 for lambda a, and that becomes 1 squared plus 1 over 1 minus lambda b equals 0. Of course, 1 squared plus 1 over 1 equals 2. Therefore, 2 minus lambda b equals 0 implies that lambda b equals 2. I don't know if that actually proved anything. I feel like I misused that theorem there, but it was the quickest way I could think of, honestly. Thinking about it now, I could have actually to find the inverse, I probably could have just augmented this with the identity matrix and then do row reductions to make A the identity matrix, and then where I was, that becomes the inverse. That makes sense. So I guess I could have done that, but it just didn't come to my mind. I actually had that written down on my cheat sheet somewhere, come to think of it. Yeah, had that kind of written there, but to be honest, for the matrices part of this exam, I didn't actually need the cheat sheet at all. The thing I wrote in there was useful. The decomposition stuff, I figured that wasn't in the paper for like the past 4 years. I thought to myself, okay, this is definitely going to come up. And spoiler alert, it didn't come up. So, bit of a waste of space, but oh well, better safe than sorry. But that's that question. Question 4. Okay, so what I just showed you was the first 50 marks of the paper. There are 5 questions on this paper, so 4 and 5 together are 50 marks. Out of 100, of course. So yeah, this question was 5, 10, 15, 23. This question was 23 of these marks. So yeah, for given polynomials px, qx, rx, we are given the following table of inner products. For example, the inner product of q and r is equal to the inner product of r and q, which equals 0. Compute the inner product of p and q plus r. So for this one, I used, what law was it? The law where it's like for inner product, u and v plus w equals u and v plus u and w. Here, I used that one there. See, I remember using, what was it? I believe I used p and q plus p and r. Yeah, p and q is 0, p and r is 8. So yeah, this is just 0 plus 8 to get 8. Seems a little like a small amount of work for 5 marks, but didn't know what else I could really do there. I believe that says compute the length of q plus r. And this one, I remember getting 0 for it. Yes, yeah. How did I do that one again? I think I remember I did like q and r plus r and q to get the q plus r and q plus r, like inner product, and then I square rooted that to get the length, and then of course q and r plus r and q is just 0 plus 0, that's 0. Square root of 0 is 0, so that's how I got that. I believe one person for this one got 64 because they squared the 8. I'm not too sure why they did that actually. But yeah, and then another person for this, I remember saying they got 51. I think it's because they literally just did r and r plus q and q. Big brain moment. Okay. See, let E denote the span of P and Q. Find the orthogonal projection. Express your result as a linear combination of P and Q, i.e., find real numbers CP, CQ, so that the projection of R is equal to CP times P plus CQ times Q. This one wasn't too bad, honestly. Just using the formula that I'd written down. Extremely messily, just there. Yeah, that was fine, to be honest. Can't remember my exact answer. I think I remember. Oh no, I remember I got CP to be equal to 2, and I got CQ to be equal to 0, I believe. And then find an orthonormal basis of the span P and Q and R, P, Q, and R. Express your result as a linear combination of P, Q, and R. Okay, so for this one, I believe I used the Gram-Schmidt formula to go from a regular basis to an orthogonal one at first. And then, what did I do after that? Oh yeah, and then I know that for an orthogonal basis, if you take each like element and put it over its length, you get an orthogonal matrix. An orthonormal basis. See, I just did that really. I remember being a bit unsure about that one. I believe I got something like, what did I get? I got like a half P Q and then like 2P minus R or something maybe. I think so, something like 2P minus R. I can't remember honestly. Oh, it might have been 2Q minus R, I don't know. I believe there was a minus R there somewhere. But we're here now. Okay, so final question of the paper. This one was 27 marks, of course. Biggest question on the paper so far. Yeah, about polynomials this time. So let's see. Let pi 2 denote the set of all polynomials on the unit interval with degree at most 2. Show that b is a basis for pi 2. 7 marks. This one was just fine. For a quick second, I actually forgot how to prove that something is a basis, but of course it's just that show that that this is a linearly independent set and that spans the entire set. How did I show that it was linearly independent? I believe to show that it was linearly independent, I multiplied out that bracket, I took scalars, took linear combinations of these three, and then got the coefficients in terms of alpha 1, alpha 2, and alpha 3, corresponding to the units coefficient, the x coefficient, and the x squared coefficient. I did that, set them all equal to 0, and then put the coefficients in like a matrix, and then I showed that that matrix is full rank, therefore it has an inverse, and that inverse basically means that all three alphas can only be 0 for this to be linearly independent, for the linear combinations to be equal to 0. So there's that. And then to show that it spans the entire space, I just kind of said that, remember, I think I got like my coefficients for the ones to be like alpha 1 plus alpha 2 plus alpha 3. And then I believe my coefficient for the x was minus alpha 2 minus 2 alpha 3. And then my coefficient for the x squared was just alpha 3. I said that since none of the equations for the coefficients of 1x and x squared are equal, you can create any polynomial of degree no greater than 2 with them, therefore spans the entire set. That was my reasoning. I don't know if that is actually like solid enough, but I didn't know what else to put there really. I represent the polynomial p of x. So yeah, basically find the coordinates of this polynomial with respect to this basis. So yeah, basically just find linear combinations of this basis that gives you this polynomial, and then put those scalars into a vector, column vector. That one wasn't too bad. I got like 16 minus 16 or something. I can't exactly remember what that was there, but I'm pretty sure that was right. I was confident about that answer. Now, I remember C messing me up because it's quite similar to A. It's a bit more general. So it's just that let's see here, consider the polynomial qx equal alpha plus beta x, under which conditions on the coefficients alpha beta is this new basis, a basis for pi 2. So I did the same kind of approach. I believe I put it into a matrix of coefficients, and yeah, I remember at the very end when I was doing my simultaneous equations, I got like 1 plus 2 alpha over beta equals 0, and then the next line was like minus 2 over beta was equal to 0, and then the third line was alpha 3 is equal to 0. And I said that, I thought I did it wrong for a second because that seemed like a little too basic, but I ended up just saying, well, I tried to say that this works for any real alpha and any real beta except beta is equal to 0, but I accidentally messed it up and I wrote alpha and beta can be any real number except 0, so I said that alpha can't be 0 as well. Messed that one up that I only realized after discussing with some friends, so oh well, nothing we can do about it now. Lost 1 mark there, definitely. D. Consider the map T, which maps with T, P of x equal to D. D is the differential operator, show that T is a linear map. I remember I was skim reading through this question, I saw the words differential operator, and because that had like never been even mentioned in like this term specifically had never been mentioned in class, I thought to myself, what's actually going on. But then I just realized it's just differentiating the polynomial in question with respect to x. That wasn't too bad. Now, in class, we used the phrase linear transformation, not linear mapping. So I was a bit confused there. Ended up just like proving that it was a linear map. I mean, I ended up just using the rules for linear transformations here, that t of u plus v must equal tu plus tv, and this. I proved these two in the general case for I just realized something. Okay, so oh, that's annoying. So yeah, basically I just remembered this is the polynomial space of degree no greater than 2. I used general vectors, general polynomials of like alpha plus beta x. I did not include the x squared power there. Rats. Okay. Yeah, damn. Oh well, but oh well. But basically, yeah, I just differentiated alpha plus beta x. And yeah, really just showed these two in with general u and v, but in the wrong degree, unfortunately. So I've probably lost a couple marks on that one as well. Find the matrix A that represents the map T in basis B, i.e. Okay. I remember while I was writing up my cheat sheet, I know the part of the notes that this part is referring to. I didn't understand it whatsoever, but I still wrote it on my sheet anyway in case I have an epiphany. And when I first saw this question, there was about 50 minutes left. And for about 40 of those 50 minutes, I thought to myself, okay, I just don't get this concept. There's no point in even trying to. And then with 10 minutes to spare, I thought to myself, you know what? I may as well just take a second good look at it. And I realized, hold on. It's just like putting I interpreted it as putting the vectors of the basis B into T and then getting that result as coordinates from the basis B. Like for example, T, let's say if you choose P to be 1, and of course T of 1 is just d by dx of 1, which equals 0. So then the coordinates of beta for 0, so yeah, using this for 0, I believe you get 3 zeros or something, I think. I'm pretty sure it's 3 zeros. And yeah, so it's just getting each element of this basis here, and then differentiating it and then writing that differential in terms of coordinates for that same basis, if that kind of makes sense. That's how I saw it as. And then a cubed. I remember because I had about 5 minutes left to do this once I found a, I had about 5 minutes left to do this question here. And I definitely rushed my calculations, which could mean I got them wrong. I remember I ended up getting a cubed to be a matrix full of zeros. And at first I thought that it meant that T is an injective linear map. But no, injective is if the kernel of the linear map is equal to the 0 vector. So yeah, I just couldn't explain that result. But yeah, that is the paper I sat today. It was 3 hours. Yeah, as I said, I thought I wouldn't need all 3 hours. I definitely did. To give a score out of 10, I'd give it about an 8. I want to say 9, but I think that I'd be jinxing it. So I'm gonna say 8 out of 10. I was happy with that, to be honest. I thought it would be worse. I was a bit disappointed that I didn't really use my like matrices stuff on this cheat sheet that much, but I guess that just means I studied well for it. So yeah, let's see here. What else? Okay, yeah. Also, my next exam is on Friday. That is calculus. Again, 9 a.m. Again, 9 hours. I'll probably bring the exam paper back as well, just to see if there's any questions that kind of that I think I should make comments on. And I believe that is it. And yeah, thank you for watching. Enjoy your day. See you in the next one.